NASA has explored various methods for managing human waste during space missions. These include the development of advanced space toilets, such as the Universal Waste Management System, UWMS, which utilizes airflow to collect waste in microgravity environments. NASA has also investigated approaches such as fecal containment, stabilization, dehydration, and long-term storage, focusing on minimizing mass and ensuring crew safety on long-duration missions. Now, let's transition to discussing my unique method for waste management in space. Anaerobic bacteria decompose organic material, producing methane gas, liquid with alkaline content, and stabilized solids. Long-term lunar missions demand sustainable solutions for waste management and resource recovery. Traditional methods would be too bulky, inefficient, and unsuited to lunar conditions. To address this, we developed the LunarBiome bioreactor, utilizing anaerobic bacterial processes to close the resource loop. Anaerobic bacteria decompose organic material, producing methane gas, liquid with alkaline content, and stabilized solids. This alkaline filtrate is then recirculated back into the bioreactor, naturally stabilizing the internal pH without relying on external chemical inputs. This closed-loop pH regulation not only enhances system efficiency, but also minimizes resupply needs, making it ideally suited for long-duration lunar missions. Unlike conventional systems, which depend on regular chemical replenishment, our method uses internally generated resources, ensuring continuous, autonomous operation. To date, NASA has not implemented this approach in its anaerobic waste management systems, making our solution a pioneering innovation. This advancement significantly reduces mission risk, conserves payload mass, and establishes a new standard for sustainable waste management in extraterrestrial habitats. During anaerobic digestion, methane gas is produced as a valuable byproduct of waste decomposition. Rather than venting it into space, the LunarBiome system captures this methane for essential secondary uses. The methane is utilized for external heating of the bioreactor, helping to maintain optimal internal temperatures critical for bacterial activity, especially during extreme lunar nights. Additionally, methane energy supports mechanical systems responsible for maintaining internal turbulence, which ensures even distribution of substrates and maximizes digestion efficiency. By harnessing methane locally, the system reduces the need for externally supplied energy sources, lowering mission costs and increasing operational autonomy, critical advantages for sustaining long-term human presence on the Moon. Solid waste on the Moon is a critical aspect of sustaining long-term human presence beyond Earth. Rather than treating waste as a burden, lunar missions increasingly view solid waste as a valuable resource that can be repurposed to support essential operations. Solid waste generated by crew activities, including biological waste, packaging materials, and structural debris, can be processed and transformed into useful materials through various techniques. Stabilized solid residues from biological waste treatment, for example, can be utilized as building components for lunar infrastructure, such as regolith-based composites for radiation shielding and habitat construction. Reusing solid waste reduces the need for resupply missions from Earth, minimizes storage requirements, and enhances mission sustainability. To design an optimal anaerobic bioreactor for lunar waste recycling, a compact bioreactor volume of approximately 100 liters is selected. The biomass concentration in anaerobic digestion systems typically ranges between 30 to 50 grams of dry bacterial mass per liter. Considering that bacterial cells are about 70% water, the live biomass concentration is around 150 grams per liter, or 0.15 kilograms per liter. Thus, in a 100-liter bioreactor, the total active bacterial biomass would be approximately 15 kilograms of live bacterial mass. Under optimal conditions, with a mesophilic environment at 35 to 38 degrees Celsius and a pH range of 6.8 to 7.2, anaerobic bacteria can process about 1 to 2 kilograms of organic waste per kilogram of bacterial mass per day. Assuming a median efficiency of 1.5 kilograms of waste per kilogram of bacterial mass per day, the total daily processing capacity of the bioreactor is around 22.5 kilograms of organic waste per day. Each astronaut produces approximately 150 grams, or 0.15 kilograms, of fecal waste per day. Therefore, the bioreactor can support the waste recycling needs of up to 150 astronauts, indicating that it is significantly oversized for a standard lunar crew of 4 to 6 astronauts. This provides sufficient capacity to recycle both ongoing and legacy waste. The Apollo missions left behind approximately 90 bags of organic waste on the moon, with an estimated average weight of 0.91 kilograms per bag, totaling around 81.9 kilograms. If one astronaut were operating the LunarBiome bioreactor to recycle this legacy waste, while also producing an additional 0.15 kilograms of fresh waste daily, and the bioreactor processes up to 22.5 kilograms of waste per day. It would take approximately 4 days for a single astronaut to fully recycle the 90 Apollo waste bags using the LunarBiome bioreactor. LunarBiome isn't just a waste solution, it's a transformative system that converts waste into energy, building materials, and life support resources, all within a compact unit costing under $400,000. Environmentally sustainable and efficient, it minimizes resupply needs and maximizes autonomy. NASA, let's pioneer a sustainable future on the moon together.